How wonderful it is to be back amongst you with the living. It's great. So, I want to thank you all for showing up for your learning. Not all of your classmates chose to do that. Many of them have extracurriculars and whatnot, and many of them also thought that Fridays, like 3 Fridays before Christmas, is somehow like optional. But in any case, let's carry on. Why do we need this like trigonometry stuff? Why is it useful? Well, this comic shows us one situation and a lot of situations where we'd love to have a certain measurement, but measuring it directly is not available to us. And then by using the power of trigonometry and triangles, we can actually get these measurements. So here, our poor student says, I need to measure the height of the tree, but when I asked the squirrel to help me carry the tape measure to the top branch, he took it and buried it with his nuts. Darn that squirrel. So anyway, and we can't climb the tree ourselves, so we would call this tree inaccessible. We can't climb it to measure it directly, but we can do things like measure the shadow of the tree and the angle that the sun is creating the shadow with, and use the resulting triangle to measure the height of the tree, which is a pretty cool idea if you think about it. That's always just like available to us out there. Now, let's take a look at the how we do the calculations. So let's go for it with that. So you can follow along and take a note or mark your quiz. I'm going to discuss each one as though this is a lesson, because this is now the lesson for today. Here is a triangle. Suppose that we have a wire that is connected to this building, all right? And it's like it's a guy wire and it's holding the building up, or well, it helps stabilize it. So there's our building. And there's the door and the handle, all right? So it helps to have these diagrams. And suppose we don't know how tall the building is because it's inaccessible, and the cable is really hard to Spider-Man your way up the side of the cable and measure it directly. But we can measure from where the cable attaches to the base of the ground and to the base of the building. And if we want to find the measure of that cable, well, we'd also need one more known. We need like two, like really, we need three knowns in this situation to measure this. We have known the angle here, it's a right angle, and we have known this angle here. So couple that with the known length, and we can solve for the length of the other side. So we can calculate this height of the building, we can calculate the length of the wire. Let's say we want to know the length of the wire. So this is our thinking process for this. Aha, an angle, a triangle. I know I can use trigonometry. It's been named tri, so it has to do with like three pointed things, so that's very useful in this situation. And then we say, I remember that there's three trigonometric ratios. Name them for me. Sine, someone else. Cosine. Tan. Tan. Okay, thank you. That's great. So we have sine, cosine, and tangent. And in these triangles, I'm going to draw a hypothetical right angle triangle. There we go. And if this is our angle of interest, so name it, call it theta, and I want to know what's sine theta, cos theta, and tan theta, we have three sides here, and each side has a unique name. And then if I were to have a ratio of two of those three things, there's actually three possible ratios. Well, there's actually six, but we only use three of them right now. So this side, we call it the hypotenuse. It's the longest side. It exists directly opposite the right angle, and it's always going to be the longest side of a right angle triangle, it's the hypotenuse. If the triangle's not right angled, we don't talk about hypotenuse anymore. That's a piece of language that only applies in right angled triangles. And I encourage you to imagine a hippopotamus. A hippopotamus is a very lazy creature, and it loves to lie on slopey riverbanks. So here is the hippopotamus. It's sleeping right now, lucky for us, because it's a vicious creature with pointy triangular teeth. And it sleeps lying on the hippopotamus. Got that idea? It's a very long creature, so it's longer than both of its legs. Okay, the legs of the triangle are the two shorter sides, and we name them opposite and adjacent. Tell me, Which one of these sides is the opposite? Not to check, tell me which one of the sides is opposite. Yeah, this side over here. We go across from the angle to find the opposite. We go next to the angle to find the adjacent. So you can think of people that live opposite you. They live across the street. You have to cross the street or you have to cross the triangle. People who live adjacent to you are right next door. So that's how we name these sides: opposite and adjacent. And then we have a nice way of remembering the different ratios with sine, cosine, and tangent. There's a kind of rhyme or many different songs on YouTube that teachers like to play for their students. You're all making me do it. Okay. All right. So we have SOHCAHTOA style to help us remember the different ratios that we're going to be setting up. And ratios, you can remember, we can set them up like fractions. So sine is opposite over hypotenuse. It's a ratio of the sides. Cosine's adjacent over hypotenuse. It's a ratio of the sides. Tangent's opposite over adjacent. It's a ratio of the sides. Tangent's opposite over adjacent. It's a ratio of the sides. That's what they say over and over and over again, so that you will see that. So now what we're on the hunt for in the context of this problem is we have here our angle of interest right here. This side is opposite, adjacent, or hypotenuse. That one is adjacent. It's right next to the angle, and it's not the hypotenuse. The unknown, this guy wire that's holding up the building, is the hypotenuse. It's the longest side. We can imagine the hippopotenuse sleeping on that guy wire. It would quite enjoy that. It would be a good substitute for a riverbank. So let's go ahead and erase all those arrows and put this problem together. So what we can do now is say we're going to use the trigonometric ratio that relates adjacent and hypotenuse. Which trigonometric ratio relates adjacent and hypotenuse? Yeah. Cosine's adjacent over hypotenuse. SOHCAHTOA. So CAH, cosine's adjacent over hypotenuse. So we use that little memory trick to remember. And you can start your solutions like this. Cosine theta equals adjacent over hypotenuse. And then go ahead and substitute in your knowns and your unknowns. So here I know the value of theta. Theta is the measure of the angle. So we're going to say cosine 43 is equal to 35, which is the adjacent, that's known, over, here's the hypotenuse P. Put that in. Now, this question is a bit challenging to solve because our unknown is on the bottom. When the unknown's on the bottom, there's kind of two roads you can go to get the unknown to the top. So let's go ahead and take a look at those two roads. The first road is just fine to use, is see that the unknown is on the bottom and say, I would like that on the top. So multiply both sides by P. When I do that, this P, which is division, will cancel this P, which is multiplication. Something downstairs is the same as something upstairs, cancels because you're multiplying and dividing by the same thing. That's like multiplying by 1. I happen to be 42 times 5 divided by 5 years old. I'm 42. So, but then the unknown is on the top of the equation, but on the other side. And it has a dance partner. Its dance partner is P times cosine 43 is now equal to 35. Well, I'd like to get all my knowns to one side of the equation and keep all my unknowns on the other side so that I can achieve my goal of solving for the length of this guy wire. P equals blah, blah, blah. So what we're going to do in that case is go ahead and divide by the dance partner. Here we are multiplying by cosine 43. So now divide by cosine 43, both sides of the equation. And then you get your answer. P is equal to 35 over cosine 43. Because these cosines will cancel. They're the same thing. And that isolates P on one side of the equation. So you finally have your equation as P equals blah, blah, blah. All right, let's evaluate it. Here's how we punch it on the calculator. And I want you to get out your calculator now and try punching it while I punch it. Because if you get a different answer, it probably means that you and I need to sit down and get your calculator set up in the correct way to interpret the work that you're going to be doing with it, or teach you how to do the keystrokes. So that's an important part of today's lesson and the rest of the time that we're going to have together, making sure you know how to punch these. Okay, so I want to punch 35 divided by the cosine of 43. On this calculator, I push 43 and then push the cosine button. That's the cosine of 43. It's saying that in a 43-degree triangle, the adjacent side is about 0.73. It's about 73% as long as the hypotenuse. When I push equals here, it does the operation and tells me 35 divided by that 0.7 whatever is about 48 meters. So P is about, and I use equal by rounding, 48 meters. I can circle that and say, therefore, the guy wire is 48 meters. Let's see. Okay, my tongue came out straight. I seem to be okay. All right. Let's erase that weird Y. Okay, there we go. So that's how we'd solve this type of problem. I promise you another way to solve them. Let me show you. If you have something like cosine 43 is equal to 35 over P, I would do it this way. I say, I don't like my unknowns on the bottom. I flip both sides of the equation. That's an inverse operation you're allowed to use. Just flip both sides of the equation. No problem. And then we go ahead and multiply by 35, both sides. 1 times 35 happens to be 35, and we get the same expression over there. 35 divided by cosine 43. And I think that's a nice thing to add to your toolkit. I know how to flip both sides of an equation. Still true. If 2 equals 2, well, 1/2 equals 1/2. I can flip both sides of the equation, no problem. 2/3 equals 2/3. 3/2 equals 3/2. Both are true. You just flip both sides of the equation. Should still be true. So let's go. Keep going. All right, next question. Candace and G are playing football. All right, if they're standing next to each other, they're in the same spot, effectively. So that's great. Candace runs 12 meters north and then turns 90 degrees and runs 9 meters east. With these questions, visualize, imagine Candace and G playing football. G has the football, Candace is running. I see Candace turn to the east, and then G throws the football on some angle. Cool. So visualize, and then draw a diagram. So I'm going to draw a diagram here. This is my north direction. Okay. So here is G. She's down here. All right. And there is this running north that happens away from her. And that was 12 meters. And then she turns, and then Candace turns 90 degrees and runs this way. And she runs how far? 9 meters. Okay? And then the football is thrown over there. Cool. So that's how we create a diagram. Grab one of these to take your note. It was a quiz, but it became a note. Okay, so now I've got this great diagram. I've labeled my knowns. I notice I know no angles. So actually, I don't really need to use trigonometry here. There's another tool that I wanted to see. Do you know to use this tool? What's the other tool that I can use to solve for how far the ball is thrown? Yeah, we're just going to use Pythagorean theorem. So I'm going to label this H for the hypotenuse, or for the hella wicked football throw that G pulls off here. Yeah, so we say H squared equals 12 squared plus 9 squared. Let's work that out. Anyone happen to know what that's going to be? 144 plus 81. The sum of 144 and 81 happens to be 225. Anyone know H squared yet? Or what H is? Sorry? Yeah, it's indeed 15. If I told you that she threw the football 225 meters, what would you tell me? Oh, wow. Person ran 12 meters and then 9 meters, and then a throw of 225 meters somehow reached this person. Yeah, that mathematically what I forgot to do is I forgot to square root it. But the reason why I'm slowing down here to say check your answer is because you start by visualizing the situation. Have you ever seen someone throw a football 225 meters? Like from here to Cameron Street Public School? Like that would be for people your age, like a pretty decent drive with a golf club. You know, like with a driver, and you hit the golf ball 225 meters. That's about 250 yards. That's a good golfer at teenage level. You know, you can't throw a football that far. So your visualization saves you when you make that mistake. The other thing that saves you is you've got a diagram here. Put your known down here. If you write 225, there ain't no way that's making a triangle with 12 and 9. 12 and 9 can't stretch that far to reach those corners. So that would help you solve the problem. You need to square root both sides. And yes, 15 squared is indeed 225. So that's the distance. So therefore, G threw the ball 15 meters. Cool. Any questions? No? Okay. Well, I could also ask you what was the angle that the ball was thrown at relative to north, but that's on Monday's topic. So we'll come back to that type of thing on Monday. Well, let's go. So Jeremiah, he's here at camp, and they're doing trust falls today. And I looked at that picture and said, that looks like he's about on a 30-degree angle, and he might be a little bit tall. Maybe he's about 6 feet tall. So he's a 6 foot tall individual, and he's 30 degrees to the horizontal right now. And I'm curious, how high is his head above his feet right now? How high is his head above the people who are catching him, in other words? So let's find out. So in these types of situations, you still want to visualize. I've given you the picture to help your visualization, but you also want to then draw a triangle. So let's draw a triangle that matches that. We're going to draw this height of his head. We're going to say heights are 90 degrees to horizontals. That's a cool thing about gravity, is a lot of things like people, when they stand up, are perpendicular with the ground. Poles are perpendicular with the ground. Trees tend to grow perpendicular with the ground. Sometimes you get cool trees that grow on angles. But if I ask you how tall is that tree, I'm basically asking how high is the top point above the ground. Still a right angle, even if the tree is growing on a diagonal, like out the side of a mountain or something. So here, we're going to have Jeremiah. This is Jeremiah's body here. This angle is 30 degrees, and we were told that he was 6 feet tall. And we want to know the height above his feet, of where his head is as he's 30 degrees lying back in the middle of this trust fall. So how are we going to solve this question? Sing the song in your head. Sine is opposite over hypotenuse. It's a ratio of the sides. And in this case, it's a ratio of the side of this side is opposite, and he is the hypotenuse. He's the hypotenuse now, falling through space. So we're going to use sine, because sine relates opposite and hypotenuse. And I notice that this angle is opposite that side. That has to cross the triangle to get it over there. So sine is correct. Sine 30 degrees is equal to the unknown that I'm looking for over 6 feet. Cool. Now this one is easier to solve because we just have to multiply by, right now we're dividing h by 6. We would like to just know h equals. So let's get rid of that dance partner, throw it to the other side of the dance floor by doing the opposite. Right now we're dividing, so we do the opposite, which is multiply. So then you'll have 6 feet multiplied by sine 30, and that's our answer. 6 times sine 30 equals h. Now, I happen to know the value of sine 30. Check on your calculators now and make sure that your calculator tells you that sine of 30 is 1/2. And if you don't get that, make sure you bring me over to your desk after this brief lesson, and I'll correct your calculator for you. Okay, sine 30 is 1/2. I'll prove it to you. 30 degrees, but I take the sine of it. See, there's 1/2, 0.5. Then I multiply that by 6 feet tall to get 3 feet. Yeah? Yes, I'm sure that will be fine. So now we know that h is equal to 3 feet, and so therefore his head is 3 feet over the horizontal. Cool. The last one is a very practical type problem. The ramp of a certain loading dock wants to be built, and we know that we need to lift things up by 1.5 meters. Okay, that's how much rise we need in total. But we're limited by the angle. The angle cannot be a ramp that's at 90 degrees is useless. That's called a wall. If the ramp were at 45 degrees, it might be too steep. You might not be able to push your goods up there. A lower ramp gives you a better mechanical advantage, but then the ramp has to be longer, the longer that angle gets. So let's find out the minimum length of ramp that we would need here. So here we go. Draw a picture. First, I will draw a ramp. And then I will draw a horizontal line representing the ground. Then I represent the height that I need to go up, and remember that the ground and height is at a right angle. This rise must be 1.5 meters, and this angle must be no more than 25 degrees. We will minimize the length of ramp by using the maximum angle. And that we don't need a proof of this at this point. You just need to be able to visualize that that's true. As the angle gets steep, bigger and bigger, the ramp will get shorter and shorter. 90 degrees would be the shortest possible ramp. It would be 1.5 meters long, and it would be the wall. And that would not be a ramp. The angle was too big. If we used a 20-degree angle, you can imagine it out here, 20 degrees, and that would be permissible, but the ramp would be longer than necessary. So we'd be wasting money and wasting space. So let's go ahead and solve for the minimum length of the ramp, which will be given by this triangle. Let's go. So here, and this is our desired thing, is the ramp length. This will still be sine. Yes, this is sine theta will be equal to opposite over hypotenuse. And in this case, we know this sine of the angle we want is 25 degrees. And we know that the opposite is 1.5. And the hypotenuse is our desired known. It's the ramp length. I would suggest flip both sides so that you have 1 over sine 25. Because sine 25 is over 1. So I can flip that. And then flip the other side. R over 1.5. And now, go ahead and get your inverse operations pen out. Multiply both sides by 1.5. That's my multiply sign. That confuses people still to this day. We use a dot to denote multiplication. A lot of math people. And so then I have 1 times 1.5. Oh, I know what that is. That's 1.5. And then I'm dividing by sine 25. I don't happen to know what that is, but it's a little bit less than half. And then, actually, I think it's a fair bit less than half. I'm going to guess like 0.4, 0.35 maybe even. And then this is going to all equal r. So that's great. We're going to find the ramp length with that expression. 1.5 divided by 25, but I take the sine of it. Oh, it turns out to be 0.42. I thought maybe 0.35, so I was kind of wrong there. And then I push equals. The ramp can be 3 point, oh, Jesus. Like you said 3.5, really we kind of want to round up here. I would say 3.6. Better to have a ramp that's slightly too long than a ramp that's slightly too short. Slightly too long, and you can probably accommodate it, no problem. Slightly too short, and maybe there's stuff you can't push up it anymore. And it's useless.
Why do you round it to 3.6?
Yeah, it should round down to 3.5, but then consider the consequences of rounding. You have a then slightly shorter ramp, and you said the angle can be a maximum of 25. Now the angle, I mean, honestly, the angle is going to be 25.02 or something like that. Like the consequences to that angle are very, very minimal. But if you are absolutely limited by that angle, make it a little longer. Also, let's take it to the nearest centimeter then. The nearest centimeter, that would be 355 centimeters here. And I think that's a good answer. 355 centimeters. 3.55 meters would be 355 centimeters. Therefore, the ramp should be 355 centimeters long. Okay, put your names on the quiz. Hand it to me so I can see how things are going. And if you didn't get down the answers, but you should have, then what I'll do is put this note on the D2L for you. And any questions and your team learn at home, absolutely hit me up by email. When I say hit me up by email with your questions, I mean if you have a question, email me your question. Sorry? Yeah, I'm going to put that on the D2L for you.